All right, so we are almost done with the training of neural networks, or I should say feed-forward, ordinary feed-forward neural networks, possibly with many layers. We have seen how to calculate the forward path, we have seen how to adjust the weights using backpropagation via the backward path in order to train our weights, and we just discussed overfitting, which is a problem in neural network learning. And by the way, concerning the overfitting problem, I would invite you to visit the TensorFlow playground and convince yourself that neural networks in fact are vulnerable toward overfitting. Take that as a little homework to create an example where you manage to overfit a neural network on the TensorFlow playground. And that is almost it. When it comes to training these models, there are a few more tweaks that I want to comment on, and this is what this final chapter in the third lecture is actually about. So let's have a look what needs our attention for tuning and tweaking. Now, first of all, there is the data. There is data preparation. Data preparation for neural networks. Well, in the vast majority of cases, data prep for neural networks is not any different than data preparation for any other type of machine learning algorithm. It's always important, starting with an explanatory data analysis to understand your data and to develop hypotheses what patterns might exist in your data using all sorts of measures, descriptive statistics, or visualization techniques that help you better understand your data. Of course, that's very important if you work with a real-life data set. And then there is variable selection that is often useful because a reduction of dimensionality helps to sustain the interpretability of models, or at least it makes a model a little easier to understand if the number of features is not excessive. And sometimes reducing dimensionality can also help to increase model performance, such as predictive accuracy. To be fair, if you set up your neural network properly, using regularization, for example, variable selection should not be needed to increase predictive accuracy. If there are features in your data that just don't add much to predicting the target value, you can get rid of these using regularization, using or tuning the regularization parameter lambda, for example. Still, variable selection can be useful for interpretability reasons. Then we have categorical data that can be a pain to work with. Neural networks cannot process categorical data in its raw format. You might need to use dummy coding, which on the other hand increases the dimensionality a lot. So you could use weight of evidence coding that we learned about in business analytics and data science to avoid this growth in dimensionality when you encode categorical variables. On the other hand, maybe you can regroup your categories so that you don't have that many levels, optimizing the regrouping using decision trees and information gain, and then use dummy coding. These are just standard ways that exist, that are part of data preparation, and that are equally important in neural networks as they are with other machine learning techniques. Feature engineering is normally regarded the gold discipline, the most important step in data preparation, creating meaningful features, drawing on all your domain expertise. In deep learning, this is a little bit debatable. Do we really need feature engineering? I mean, after all, the promise of deep learning is that deep networks are capable of learning features automatically, learning a good representation of the data to facilitate the modeling task to achieve high accuracy. But yeah, it is debatable, and I guess it also depends a little bit on the type of data. When you work with unstructured data, when you work with image data, for example, we do know that certain patterns just exist in image data. Normally, if you get to see an image, you will be able to perform the task of detecting whether this image depicts a human face easily. You can do that. It's maybe hard for us to really explain or even program how we do that. It's not really programmable. We can't write down how we do that, but we can do that. And this sort of proves that there is structure in an image, and if we understand the structure, then we can tell whether an image is showing a face or not. The structure is there, and it's only about, the learning is only about identifying this structure. If it is there, a deep network should be capable of identifying the structures. That has been shown many times to work very well in computer vision. And also in natural language processing, where language has certain structures. They are very complicated semantic patterns, syntactic patterns that exist in language. They are very complicated, but they exist. And if you are able to speak a language fluently, then you know these patterns, and they exist. And a complicated deep neural network should be able to also detect these patterns from data. If, on the other hand, you think about a financial time series, the price of your favorite stock, for example, yeah, what patterns really exist in this price time series that can be projected to the future? Are there any patterns for start? Or is the market fully efficient and there is no information in past prices that would allow you to predict the futures? If there is no structure in the data, a deep neural network could not detect it. Or generally, if the pattern that exists in the data changes a lot over time, well, it is a lot more difficult for a neural network or a deep network to really learn features automatically. And if you, knowing the domain very well, have an understanding what might be a good feature, then feature engineering is still highly useful for neural network learning as well. But it's a bit debatable. In fact, again, you could play a bit with the TensorFlow playground, referring to this spiral problem. Maybe some of you have found a good solution to the spiral problem, or found a network architecture that classifies the spiral data with high accuracy. And if you make your model complicated enough, that is generally possible. But what's also interesting with the spiral data set, if you try it out, to add some transformation of your inputs, which TensorFlow allows you to do, then you can actually solve the spiral problem quite easily with not too complicated neural network. So feature engineering, this is what I'm trying to say. It has value also when you work with neural networks. Okay, so in a nutshell, what you do with any type of machine learning model, how you prepare your data, holds true in neural networks. What is specific about neural networks? One data preparation step that we often perform is the normalization of our input data, where we take all the variables that we have, all the features that we have, and project their values so that they are all in a common range. And the two popular ways to do that are the standardization or the Z transformation. You can also call that a Z transformation, what you see here, where you subtract the mean from your feature and then divide by the standard deviation. And it's called Z transformation because this X nu is, after the transformation, a variable that should be standard normally distributed. So it has zero mean and unit standard deviation. Because of that, pretty much all the features in your data after this transformation should reside in a somewhat similar interval. And you also have min-max scaling, where you can just control, where you have full control over the value range of a feature and in which value range you want that feature to be. If you just subtract the minimum of a feature from your data value exalt and then divide by the range, the maximum of that feature minus the minimum, then your new feature values will always be between 0 and 1. But you could rescale that a little bit, for example, to have all the features in a range +1 to -1. The point is they're all in the same range. And that is often useful. That is what I typically say in the business analytics lecture. That is often useful simply because it helps you with diagnosing your models. It helps you with interpreting model results. If you think about a regression model, simple regression model, y equal to beta 1 times x1 plus beta 2 x2. You have two features, let's say x1 equals age and x2 equals salary. And you estimate a regression model on some data and you obtain values for beta 1 and for beta 2. We should probably add an intercept to our regression. Then if you don't scale or normalize your input values and you observe that the coefficient beta 1 is a lot larger than beta 2, that's a bit harder to interpret because age naturally will have much lower values than the feature 2 salary. And this different scaling of the features and their respective importance for predicting y, both these pieces get mixed up in the regression coefficient beta if you don't scale your data. So simply by observing beta 1 to be larger than beta 2, you could not make the point that age is more important than salary. That would be flawed or a flawed interpretation. If you normalize your data, however, and if age and salary after the normalization are in the same value range and you then observe beta 1 to be a lot larger than beta 2, that is a different story. That gives you a strong evidence for age being the more important predictor compared to salary. Well, should that be the case? So this is just to showcase how normalization is often beneficial for interpreting models. In neural networks, however, this often useful is too mild a formulation. And rather the other part, sometimes essential. That typically is true for neural networks. You must normalize your inputs, or at least there is strong reason to do so. And let's examine why this is the case. Imagine you have a data set with some features that are not scaled. So the values of one feature are much different from those of the other feature, as in age and salary. Then your error surface could look somewhat like as shown in the left plot. And it is worthwhile to spend a little time just looking at this plot and making sure you really understand it. We have two features and they get each get a weight, W1, W2, and we see this shape of the error surface, how changes in W1 are a lot larger compared to W2 when we basically walk on one of these ESO cost curves. And if we scale our data on the other hand, and both features exhibit a similar value range, the error surface would look more as shown in the right plot. And now the natural question is, so what? So we have different shape of the error surface if we normalize or if we don't normalize. The point is that think about gradient updates. Think about how easy or how hard it is to find the minimum of this loss function in this error surface to find the sweet spot right in the middle where the loss is the lowest. And it depends a little bit on the starting point. If we are lucky with our initial weights that we sample, maybe randomly, maybe we sample an initial set of weights right here. That would be very nice, because then if we do gradient updates, we would go straight to the sweet spot. That's nice. If we are a little less lucky with our starting points, well, it could actually be the case that we need to, so that would be a beautiful situation, but there is no guarantee we are that likely, right? It could be that we start somewhere here and then we go here, and then from here we go to here, and then from there maybe here, and then from there with the point, so we would go to here, and then from here to here, and from here we would basically go, well, zigzag, well, maybe to here. Okay, and then finally we are there. We would typically zigzag a lot more around in this error surface, and it might be, depending on the initial weights, much harder to find the minimum. And you see how this is different in the right-hand side. In this picture, no matter where you start with your initial weights, you can start here, you'd go straight to the sweet spot, you can start here, and again you go straight and always arrive easily at the minimum of your loss function. And therefore, the shape of your error surfaces matters and makes training easier or more complicated. And input normalization helps with simplifying the task of the training algorithm to find the minimum of your error, of your loss function. So this was a visual explanation, or rather a visual intuition, why input normalization is helpful. We can be a bit more formal if we remember backpropagation and how training works by gradient descent. Here you see once more our common three activation functions that we use to introduce nonlinearity in our networks: the sigmoid, the hyperbolic tangent, and the rectified linear unit. And by now you understand how the derivative of these activation functions affects backpropagation, and how the derivative of the loss function shows up in the calculation of our gradient that we use, or that we need to train our neural network. And well, essentially the problems that can occur with regard to input normalization, they hold true for each of these activation functions, although to different magnitude, and it's easiest exemplified in the case of the sigmoid functions. If we use the sigmoid as our nonlinear activation function in the hidden layers of our neural network, let's consider this case for simplicity. The issues pretty much remain the same also for the hyperbolic tangent and the ReLU function. So considering the sigmoid, we once more have this function and its derivative. And the sigmoid function affects the forward path, and the derivative we need in the backward paths, which is just the product of two sigmoids. And you see the red plot, or the red line, showing us this bell curve, which is the derivative of the sigmoid, or g prime of that. And now we can reason what happens if we have a feature that is unscaled. The values of that feature just go wild, like salary. We have something from, I don't know, we have a data set from our customers, maybe the minimum salary among these customers is 2,500 euros per month, and maybe the maximum salary is something 12,700 euros per month. We have a pretty wide range of values that show up in our feature. Well, and it's very unlikely, right, that the feature values are naturally very close to 0 or 1. No, well, sorry, forget about that. If we don't scale our feature, then by putting it through the sigmoid, if we input a value, salary value, into the sigmoid function, salary is always positive and typically high. Well, for a feature salary, if we put it through the sigmoid, the values that we get as the output of our hidden unit will always be 1. Any possible salary value that we would put through our sigmoid function is mapped to a value g of salary will be equal to 1, just because of the range of that feature. And you can imagine how this is detrimental, because how would the network learn to distinguish between two customers, even if they have very different salaries, since the output of our hidden unit will always be the same, it will always be 1, the customers look exactly alike, the two different customers with different salaries. And that is the problem. We can also look at the derivative then. If in the forward path we always have as output of a hidden unit a value of 1 because of an unscaled feature, then the derivative of the sigmoid approaches 0. Now if the derivative is 0, and remember the calculations in backpropagation, we had something like the gradient of j of w with regard to some weight was equal to the derivative of our loss function with regard to the network forecast. So we had something like j of delta j with regard to delta y hat. And then we were saying that y hat in turn is the result of some hidden unit h, and where we then had something like, delta h with regard to delta z, which was the input to the hidden unit, and then finally we had something like delta z with regard to delta w. And well, this was just an example of how these change of derivatives look like in backpropagation. And if this guy here, the derivative of the output of a hidden unit with regard to the input, this is exactly where we would need our sigmoid derivative. And if that is equal to 0, and it would be equal to 0 if we input some large feature values, if that is equal to 0, then obviously just looking at the gradient of the loss with regard to the weight, this whole gradient becomes 0. So that implies right? But if the gradient is 0, how do we want our neural network to learn something? Because now remember, if you add to the picture the gradient update, let's add the gradient update, where we have w is w minus learning rate iter times the gradient. If the gradient is 0, if that is a big 0, then our weights don't change anymore. So essentially we have w equal to w when we update our weight. There is no change. No change means no training. Our network weights don't change a lot. Of course, this is an extreme situation that all the components of the gradient, remember, in a neural network we have many weights. So this gradient vector will be very, very big in a real neural network. It has all these weights. But if many of these weights happen to be 0, then learning will be extremely slow, or it might even be impossible. And these zeros, they occur because the derivative of the sigmoid is 0, or gets close to 0 very soon if the values that we input are too large. This is because of the value range of the sigmoid's derivative that you see depicted here on the slides. And this should help you to understand how unscaled features impede neural network training. And this is why for neural networks the normalization of the input features is not only often useful, rather it's essential. You can make the case that it should not be needed theoretically. Theoretically, the neural network should be able to adjust the weights and the biases, don't forget the biases, you have these as well, in such a way that you can still learn the different value ranges of the input features and then input them in raw format. From a purely theoretical point of view, that should be possible. But, well, from a practical point of view, scaling the inputs is highly recommended and very likely to speed up your training a lot. And we just examined why that is the case. You will avoid this saturation of the neuron. Saturation means that you reach the saturation level of your activation function, which for the sigmoid, for example, is 1. And you have seen how an output value of 1 comes quite easily if your input to the sigmoid is something that is 4, or, well, even with an input of 3, right, you're almost here. If you input 3 to the sigmoid, you are almost at 1. So you very soon run into the saturation level of your activation function with the sigmoid. With the hyperbolic tangent, things are a little bit different. And with ReLU, yet entirely different story. The hyperbolic tangent essentially suffers the same limitation as the sigmoid, only that its derivative is larger. So it might be a little more robust, but essentially you have the same problem. Whereas with the ReLU function, if you input a positive value, the derivative is always positive. It doesn't go to 0. So in that regard, the ReLU is a little bit more robust here and might not require input normalization as much as a neural network, where as activation function you use 10H or the sigmoid. Which is one reason why today the ReLU function is the standard choice, unless you have reason to use something else. So theoretically not necessary, but practically useful. Avoids neuron saturation, speeds up training, avoids getting stuck in local minima. That goes back to the introductory example with the error surfaces, where you just have a smoother error surface if you normalize. And it also enhances the efficiency of weight decay. That's another good point. Remember weight decay. Weight decay was we add a penalty to the neural network. Weight decay could be an L2 penalty, where we penalize large coefficients of our features. If all the features have the same value range, then all the weights then the weights in the neural network, especially in the input to hidden layer, they do not need to adjust for different value ranges of the features, so that their magnitude can really focus on the importance of that features, as opposed to capturing its importance, but also its value range in comparison to other features. This is what I was showing with my regression example, right? So the penalty that punishes large feature weights, you wanted to punish the importance of the features or the lack of importance. You do not want the weight to pick up the range of the feature. And this is why weight decay also is more effective if you normalize the inputs. So long story short, you definitely want to normalize your inputs in neural networks. And how you do it depends a little bit on the activation function. While there is wide agreement that you should do it, there is no golden rule how you should do it. In many cases, using just the Z transformation should work okay. Although with that transformation, the idea is that all your features have zero mean and unit variance. In that case, it's not entirely unlikely that you will observe certain feature values that are large, that are 3 or 4 or larger. A standard normally distributed variable will show these values in the extremes and the tails, and these values would already run into the saturation level of your sigmoid or hyperbolic tangent function. However, these values for a standard normally distributed variable are not so plausible, they are not so likely, and the majority would be closer to the mean of 0, where you have a good discriminatory ability of your sigmoid and hyperbolic tangent function. If you want to be sure, however, you could use the min-max scaling, or you could scale your features to -1 to +1, which is exactly the value range of the hyperbolic tangent. If you use that activation function, it's common practice to scale your features to this range, or a little less than that. You might wonder, why would I use a little less than that? Why would I use something as -0.7 to +0.7 as feature value range if I use the hyperbolic tangent? Well, if you think about it, to carry out min-max scaling, you compute the min and the max of a feature. And the min and the max that you observe in your training data is not guaranteed to be the min and the maximum that you will see in future data, in your test data. So it is a good idea to leave a little bit of a leg room in the scaling and scale your features to these intervals for the hyperbolic tangent or the sigmoid functions. And the -0.7 and the +0.7 is not set in stone. If you like 0.8, a little better here is range, or even 0.9, do so. But generally, considering that the training data is only a sample and that you compute the minimum and the maximum that you need for your standardization of the mean and the standard deviation that you need for that transformation from the training sample, it is a good idea to leave a little bit of room and don't exceed the whole value range of your activation function. Where again, the redo should be a little bit more robust here, because for any z greater than 0, it has positive gradients. That was input normalization. Another point, a different point, concerns the initialization of your weights in the neural network. Theoretically, shouldn't matter much. It's just a random starting point from which you start your journey. But yeah, if you initialize your weights randomly, you might be unlucky. And being unlucky means that you start from a point in your error surface where it is just very difficult to locate the next minimum. And the picture shows one such point where we basically start at a plateau of our error surface and then might have a hard time to find the next minima of the loss function with regard to the weights. So bad initial weights can slow down your training. They might even prohibit it altogether if you are really unlucky. So that raises the question, how should I do it? How should I initialize my weights, or how to find good weights, or what actually are good weights? And that question has been examined in some research, and some approaches toward weight initialization have been proposed that should hopefully give us a good starting point for training. And to fully understand the consequences of bad weights, or to appreciate that, first of all, remember that the forward path in a neural network is essentially a chain of matrix multiplication. So we always have input times weights, added nonlinearity, times new weights, added nonlinearity, times new weights, and etc. We have these chains of matrix multiplications within any neural network. The deeper it is, the longer this chain. And you can, if you wish, do a little experiment. Since a neural network essentially is just a bunch of matrix multiplications, you can just draw some random numbers and draw some weight matrices and then simulate the forward loop in a neural network. You find some code in this blog, and I also recoded that in the little notebook that accompanies this slide book. So you find it on GitHub, where we just imagine a neural network that has 100 layers, so it's a pretty deep network, and in each of these layers we have 512 hidden units. So this is already quite a monster network, right? So we have 1, 2, all the way to, this is 1, 2, all the way to 512 hidden units in this network, and then we have that 1, 2, 3, 100 times. It's really a monster network. And I was leaving out nonlinear activation functions just for simplicity. They do not change everything in this toy example. And if you draw your input data randomly from a standard normal distribution, and if you draw your random weights also from a standard normal distribution, every weight in this monster network you draw from a standard normal, you can compute the forward path and see what happens. It's just a little for loop that you need here. You can expect your code for I in range 100, so you perform 100 iterations in this loop, and within this loop you randomly sample your weight from a standard normal distributions of the right size, and then you multiply your input x with these randomly sampled weights, and you update x. So x changes with every iteration of this loop. That is important. You draw the initial sample of x once, and then x is going to change in each iteration of this loop. It's getting multiplied with a random set of weights, and after this loop you can check what's the mean and what's the standard of the deviation of these weights. And maybe you have a guess what the corresponding values might be in tendency. You can try it out for yourself if you wish. And what you are going to see in a nutshell is that 1 out of 2 possible scenarios can occur. One scenario is that the initial weights are too large, and I'll leave open what too large means. So a possible outcome is that your activation signal grows layer by layer and approaches infinity. So the mean and the standard deviation that you get after running these experiments are just some obscenely large values. And another possible situation is the opposite, that the initial weights that you randomly sample from your standard normal are small, which results in the activation signal, the outputs of the hidden layer units, getting smaller and smaller with every layer, and shrinking with each layer, and then they approach 0. So it's something between 0 and infinity that you will have at the end of the forward path through this monster network. Okay, and now the question is, why does that matter? And again, it's easiest to to understand that when considering the sigmoid function, that is shown here one more time, if the output of our neural network is, well, infinity, this means the sigmoid is flat. We are somewhere here. Well, infinity is much farther to the right than what we see here, but we are, let's say the infinity is black color. So this means we are somewhere in that range. The output of our neural network, of a sigmoid, is flat. Its gradient is 0, and we have seen what 0 gradient means. Very difficult to train that network. What happens if the other situation occurs? The initial weights are small. Sorry, red is a bad choice. Let me pick green. Or rather blue. Green sort of signals something that is good. This is not a good situation either. If the initial weights are too small, so the output of our neural network is essentially 0. Now, if in a range where that is 0, the sigmoid is linear, or it's almost linear, right? At a value of 0, the sigmoid is almost linear in this range, isn't it? So either we are in the saturation level, having to cope with 0 gradients, which impedes training, or we face a situation where our sigmoid is, well, essentially reducing to a linear function. And the problem with this is that if the sigmoid is somewhat equivalent or behaves like a linear function, how should it be able to introduce nonlinearity? It can't do that. So our network becomes more and more unable to detect nonlinearity in the data. So, so here we have the problem of difficulties in capturing nonlinear patterns. Yeah, well, and the other problem was the problem of having basically 0 gradient. Well, no, sorry, we're not happy about that. We don't like 0 gradients. What's wrong with me? Today, no. We find that extremely disappointing because we can't really update our weights in the scope of backpropagations, as we have seen before. So both is bad. And what was the problem again? We initialized our weights randomly, and at least if we have then many consecutive matrix multiplications of input times weight matrices, we have seen that it's quite possible and will often be the case that we end up in one of these bad situations. One way to avoid this is to initialize the weights not randomly, or not by just drawing them from a standard normal, but to use an approach called Xavier initialization. And the merit of that is explained in detail in this paper by Glorud and Bengio. So they are arguing that this problem of explosion of or vanishing of the activation levels, that this problem, it's rooted in the variance of network weights. And then they explain in detail that if you imagine a hidden layer with k neurons, you have a hidden layer, you have k neurons in that layer, and you initialize these neurons using the standard normal, as we just did in our example, right? And then in the next layer, the input is calculated as a weighted sum over the k activation values from the previous layer. You have k neurons in the layer. In the next layer, the input to your neuron is calculated as an aggregation of these k neurons of the preceding layer. Then you can show that actually the variance in the next layer is approximately equal to k. So make sure you internalize that. You have a layer and you initialize the weights from a standard normal, where the variance is 1. And you have k units in that layer. In the next layer, you can show that the variance across the layer weights is equal to k, so all the way from 1 to k. And then in the next layer, it would be k squared, and the variance grows and grows and grows. And this is what is causing this problem of ending up with zero or infinite output signals that we found out in our simulation previously. So the remedy to this problem is to solve this increase of the variance of network weights. And one way to do that is, one way to approximately have constant variance when passing layers in the forward computation is to basically just scale down the variance by dividing with the number of input nodes. That was the initial proposition, and then later on people realized that you can do it a little bit better if you normalize the variance by considering not only the number of incoming nodes but also the number of outgoing connections, or incoming connections, not nodes, and outgoing connections. And this is why you see these two formulas here. And that is basically a way by just initializing the weights such that they obey this normalization of the variance, you can fight this explosion or vanishing of the activation levels in deep neural networks. You just account for the number of incoming and outgoing connections. And yeah, if you initialize your weights, then of course you can make sure that the variance is downscaled in that manner. And an approach that does that is called Xavier initialization. So this is something like an option that you will find in deep learning libraries, where you can control the way in which weights are initialized in your neural network. And that was not the end of the story. You note that the paper was published in 2010. Of course, some more has been done. For example, just to note, the Xavier normalization is somewhat geared toward sigmoid and hyperbolic tangent activation functions in the neural network, while the ReLU function behaves a little bit differently. So in a paper that came out 5 years later by he and colleagues, they were proposing k-mean initialization, which is a different approach that is somewhat more suitable if you configure your neural network to use a ReLU activation function. Well, so you would also find this choice in a neural network library. Feel free to read the paper for some more details. I want to skip over that, just to remind you of yet one other thing. We have talked about the normalization of the weights, of the initial weights in the neural network, which is fine, and we have seen how that is important. We've also talked about the feature scaling, and note that these two things have something in common, because the feature values and the weights, they get multiplied. And then we have seen if the values get too large that result from these multiplications, we find ourselves in trouble. Our neural network has problems with learning, gradient updates gets impeded, etc. We have seen ways to address that, normalizing the input features, initializing the weights in a proper way, using Xavier initialization, for example. But, and here comes the big caveat, we have no control what's going on within the training so far. We can initialize our weights in a smart way, yeah, to avoid saturation. We can centralize our input data to avoid neuron saturation, yeah, but no direct control over the inputs of deeper layers. And for these inputs, we would also want to avoid that they grow too large or become too tiny or become zero. Because if they do, then these latent features that get learned or emerge at some point in the deeper layers of our neural networks, they could grow too large and cause the very same problems that we've just been experiencing. To avoid that, there is an approach called batch normalization. Batch refers to the batch in batch gradient descent or in mini batch gradient descent, where you basically normalize the outputs of a hidden layer before you put them into the next hidden layer. And you normalize them in such a way that they fall into the interval of your activation function, which is once more shown here on the picture. Again, using the sigmoid for illustration, where for the sigmoid we know that we would like our inputs somewhere in the range, well, from -1 to +1 maybe, where we have this range where the gradient is clearly non-zero. So that would be proper training, would be allowed here. And then we normalize our weights to this range. No, not the weights. We normalize our input to the next layer, which is the product of the previous layer's outputs times the weights. That is what's called activation inputs here. Activation input. What's the input to the neurons in one layer? And the input to these neurons will be the outputs of the neurons of the previous layer, aggregated and multiplied by the weights. And this is what we normalize, so that it falls into a certain value range. This approach is called batch normalization. And you will see soon that if you build a neural network, for example using Keras, then you have the opportunity, when designing the architecture of your neural network, to add a layer which is a batch normalization layer. So you have one layer, one typical hidden layer, and then after that layer you can add a batch normalization layer to make sure that the outputs of the previous layer don't grow too large before they go into the next layer. And it's closely connected because it always has to do with adjusting the weights or the feature values, which are multiplied, such that they fall into a certain range that our activation functions like and don't have problems with. Now, these were the tweaks that you should know about. Normalizing the inputs, initializing weights in a smart way, and maybe adding a batch normalization layer every now and then to make sure that in the deeper parts of your network where you do not have control over inputs and weights, because all this is learned, that you still not have values that are too large or too small for learning. Tweaking. Now, tuning. I want to comment on the tuning of neural networks. Neural networks belong to the family of semi-parametric models. They are parametric in that they have a functional form which is parameterized, and the parameters are our weights, as you see here. And it's probably a good exercise if you write down the equation that would correspond to this neural network here. But I realize how we have done it, so I won't go there. You see it here for one hidden unit. And the point to make is just, it's a parametric function. And the reason why a neural network is a semi-parametric model is that the specific form of this function, this parametric function, depends on the network architecture. It depends on the number of layers that we have, the number of units that we have in each of these layers, these decisions that we as analysts have to make, they govern the shape of the functional relationship between the inputs and the outputs that the neural network represents. And because of these degrees of freedom, it is a parametric model, but we can effect or we can control the parametric form. Neural networks as a family cover numerous parametric models, so they're semi-parametric. And this means that when setting up a neural network, we have to make a lot of decisions how we configure our network. And in class, I would like to discuss that with you, see what decisions you would now be able to come up with. Unfortunately, we are not in class, so here's the answer. Or, well, the answer, these are some examples of architectural choices that you will have to make. Most prominently, what is the number of hidden layers? That's a decision that you will have to make when designing a neural network. Similarly, how many units do I want to have in each of the hidden layers? You have already seen that if you followed my advice and played with the TensorFlow playground or spent some time there. Then there is the hidden layer activation function. Of course, you can decide whether you want to use sigmoid, 10H or ReLU. As I said, quite often nowadays you use the ReLU function, as it's a little bit more robust towards all these issues that can impede the training of the neural network with saturations and zero gradients and etc. But still, for certain type of problems, the 10H might work just better. Personally, I don't see much value of using a sigmoid function as activation function, other than for didactic purposes when explaining the problems that might occur. So the decision typically would be between ReLU and the 10H. And again, play a little bit around on the TensorFlow website and look at the shapes of the decision surface that you get eventually when building neural networks that use ReLU or 10H activation. Regularization is important, definitely. Dropout is something that's very common when you work with bigger networks, deeper networks. Then you want to consider dropout, but you still would have to decide on the dropout rate. 0.5 being a common default, but clearly there is no guarantee that the default is the best choice for your problem. Do you want to use early stopping? Question mark. Yeah, typically this is a good idea. There's probably little reason to not use early stopping unless you have very little data. If you have very small data set, then, reserving this additional validation sample that you need to do early stopping, that is maybe too costly. That will be the only scenario where you might not want to use early stopping. At least for dropout, you could also decide per layer which dropout rate you want to use to make it even more complicated. We talked about weight initialization. Normally, you would not want to use just randomly initialized weights for the problems outlined. Can use Shaver or Cayman. Batch normalization, that's a bit more difficult. It's a layer that you add to your architecture. You could routinely have a batch normalization layer after every proper hidden layer. As a matter of principle, batch normalization should not cause any problems. So maybe that is a reasonable choice here. And then when we talk about the training, you have yet more parameters that you can set. Which training algorithm do you use? How many epochs do you train? What's your learning rate? Do you adjust the learning rate during the learning? What about momentum? We haven't detailed momentum yet. Again, refer you to the corresponding tutorial session. So many degrees of freedom. which make neural network learning complicated and dependent on your experience. In BADS, in business analytics and data science, we learn about grid search as a versatile approach to address this tuning problem, how you organize your model tuning, defining candidate values for the hyperparameters or the metaparameters that your algorithm exhibits, and then trying out all the combinations of different candidate settings for the hyperparameters and empirically finding out which one works best. That was called grid search because you have this search grid if you have only 2 hyperparameters. Easy approach. Just for deep learning, it normally does not work. On the one hand, you have too many hyperparameters, as we have just seen. For many of these, there are many plausible settings, so the number of combinations is just too large. And also, training a deep neural network can be quite time-consuming. So on the one hand, having many possible configurations in a grid, and on the other hand, needing a lot of time to evaluate a single cell in that grid, that is a very bad combination. So grid search would typically not work. What some people do is they just manually try out a bunch of settings using defaults for start, then focusing on one decision, let's say how many layers, finding a good setting for the layers, then they fix the how many layers decision, continue with another decision. That's a rather manual process. Sometimes I've seen that being done. A possibly interesting approach is random search. Once again, going back to a paper authored or co-authored by Bengio. They realize that grid search is prohibitively expensive for deep neural networks and propose random search as an alternative. The idea of this algorithm is that for each of the hyperparameters, you basically define a distribution of candidate values, and in the Backstra and Bengio 2012 paper you find recommendation what might be a good distribution for different types of input parameters. And then you would sample input parameters from that distribution. You run a neural network and you get a result. You get some performance statistic of your neural network, something like a squared error as in grid search. And then based on that, you sample a new configuration of the neural network, each time focusing on the more promising and more likely range of candidate parameter values. Start from a random initial solution, sample a new solution, compare new and old results, and repeat that. The papers show that you typically need fewer iterations than grid search to find a good value, because the sampling is somewhat smarter. You emphasize search regions where you have seen good performance, which is something that grid search does not do. In grid search, you just define your grid a priori and then fully enumeratively search through every possible configuration of candidate hyperparameter values. Those, and no matter whether these candidate hyperparameter values give you good performance or not. And in random search, you capitalize on this information that a certain configuration has given you a good result, and then you would increase the likelihood of sampling a new hyperparameter value in that region, which is exactly what this picture is meant to show. Something I haven't got a slide on, but you might want to check that out. There is a Python library for Bayesian hyperparameter optimization. If you want to try that out, just run a search for hyperopt. That's the Python library to do with Bayesian model selection or Bayesian optimization for model selection. Sounds quite interesting. I haven't tried that out empirically, to be really honest. The idea is a bit similar to random search, that you want to guide your search for good parameters to on the one hand, have a decent exploitation of the parameter space, but on the other hand, focus your attention on promising regions of the parameter space. It's built on top of Bayesian principles, and it promises to need even less iterations to find good hyperparameter values. Well, that translates to it promises to need even fewer neural networks that you actually train on your data. An iteration in the search algorithm translate into training one neural network with a given set of candidate hyperparameter values, right? HyperOpt promises to need less iterations to find good solutions compared to random search. Random search nowadays is already widely implemented, so you easily have access to that in standard Python libraries. For HyperOpt, I think this is not yet the case. You have the HyperOpt package and you can use that package, and it's easy to use, I figured, but it will be a little bit more difficult compared to random search or grid search, which is available in scikit-learn. Right, and that was it. Let's sum up the session on neural network training. What were our key learning goals? Well, I wanted you to know about the steps that are involved in training a neural network and a deep neural network. We have seen all these steps, I believe, starting off from backpropagation as the key part in the training, but then we've also looked into some other issues concerning regularization and how to initialize weights, for example. We have seen that neural networks are trained by gradient-based methods using backpropagation, and we have just seen that in addition to that, building a neural network model also requires us to make many decisions on the hyperparameters and other tweaks that we can apply or not apply, and it's just, or can be, a fairly complicated endeavor. So what are the things for you to do? What is your homework? I would encourage you to read up on backpropagation. There is a blog by David that I cite, but as I was saying earlier on, you definitely want to watch the video from 3 Blue, 1 Brown. You could also further refresh your experience and knowledge on stochastic gradient descent or gradient descent based methods. There is a very nice blog by Sebastian Ruder for that purpose, just to better understand these training algorithms. Good understanding of them will help you to diagnose what goes wrong in neural network training, if something should go wrong with your networks. And concerning the what is next part, well, yeah, we used to have a session on autoencoders and generative models, but given that the summer semester is 1 week shorter, and given that I realize how I spend even more time than in normal lectures on my slide books, well, this session is not going to take place. You have the material available if you're interested in, but I won't comment on that, and it's also not relevant for the final assignment. Instead, our next chapter will be that on sequence learning, where we introduce a novel type of neural network, the recurrent neural network, which differs from the one we've got to know in this session by the type of hidden unit that we use. So we will learn about recurrent cells and how then a neural network is built of these recurrent cells. Till then, I wish you all the best, and I look forward to see you in the next video. Thank you very much for your attention.